At the edge of a downtown block, a maintenance worker unlocks a rooftop access door just after sunrise. The surface is covered in gravel, ventilation units, and a series of raised ledges along the perimeter. Near one of those ledges, a shallow depression has formed lined with small sticks, fragments of debris, and a few feathers. From a distance, it doesn't appear constructed with precision. But two birds remain nearby, positioned at opposite corners of the roof, scanning in different directions. Their presence is consistent, day after day. This is not an accidental use of space. It is a repeated pattern that emerges across many cities, where hawks occupy tall buildings not as substitutes for natural habitats, but as viable structures within a constrained environment. The behavior begins with elevation. In open landscapes, hawks rely on height to expand their field of view. Height increases detection range, reduces blind spots, and allows earlier identification of movement. In cities, natural elevation points such as cliffs or tall trees are limited or fragmented. Buildings, however, introduce a consistent, vertical structure across large areas. They do not replicate natural terrain, but they provide a similar advantage: a stable, elevated position with unobstructed sightlines. The rooftop ledge functions as a vantage point. From this position, a hawk can monitor multiple zones simultaneously: streets, alleys, open parking areas, and even the movement patterns between buildings. The consistency of these surfaces matters. Unlike trees, which sway or lose foliage, buildings remain structurally stable across seasons. This reduces variability in perching conditions. However, elevation alone does not explain nesting behavior. Nesting introduces a different set of constraints, particularly exposure and access. A viable nesting site must balance two competing factors: accessibility for the parent and inaccessibility for threats. In natural settings, cliffs provide this balance by limiting approach routes. In urban environments, tall buildings replicate this condition. Through vertical isolation, the higher the nesting site, the fewer the viable access paths for ground-based predators or disturbances. Human activity, while present, is typically concentrated at lower levels. Rooftops, especially those without regular maintenance traffic, remain relatively undisturbed. This creates a predictable pattern of low interference, which is critical during nesting periods when repeated disturbance can compromise viability. The structure of the building also plays a role. Flat rooftops with ledges or recessed corners create microenvironments that reduce wind exposure. Wind, at higher elevations, introduces instability. Eggs and young birds are vulnerable to displacement, and excessive airflow increases energy costs for thermoregulation. By selecting areas with partial barriers such as parapet walls or equipment enclosures, hawks reduce direct wind impact without losing elevation benefits. The materials used in nest construction reflect the available environment. In urban areas, traditional nesting materials are often supplemented or replaced by debris, small sticks from nearby trees, but also wire fragments, insulation pieces, or other lightweight materials. The selection is not aesthetic, it is functional. The goal is to create a stable base that resists movement under variable conditions. Another constraint emerges from food access. Urban environments support dense populations of smaller birds, particularly pigeons and starlings. These species concentrate around consistent food sources, public spaces, waste areas, and human activity zones. From an elevated position, hawks can observe and predict these movement patterns. Hunting becomes less about searching and more about timing. The proximity between nesting site and feeding area reduces travel distance. This is significant during nesting periods, when adults must repeatedly deliver food. Shorter distances reduce energy expenditure and allow for more frequent feeding cycles, increasing the survival probability of the young. However, proximity also introduces competition. Urban areas often support multiple predators, including other birds of prey. The selection of a nesting site on a tall building can function as a territorial signal. The visibility of the location combined with repeated presence establishes a defined area of control. This reduces overlap with competing individuals and stabilizes access to local food resources. There is also a temporal component. Urban environments operate on predictable daily cycles. Human activity peaks during certain hours, while quieter periods occur at night or early morning. Hawks adjust their activity patterns to align with these cycles. Nesting on a building allows them to remain stationary during high disturbance periods, and increase activity when conditions are more favorable. Lighting conditions in cities extend into nighttime, But hawks do not rely on artificial light for hunting. Instead, the extended illumination indirectly influences prey behavior, keeping certain species active for longer periods. This can shift the timing of hunting opportunities, without requiring adaptation in sensory mechanisms. The choice of tall buildings also reduces variability and environmental risk. Natural nesting sites are subject to seasonal changes, branch loss, tree fall, erosion. Buildings, by contrast, maintain structural integrity over long periods. This consistency allows hawks to return to the same nesting sites across multiple seasons. Reuse reduces the need to locate and evaluate new sites, conserving time and energy. Over time, this leads to site fidelity. A nesting site that has previously supported successful reproduction becomes a stable option. The accumulated materials from previous nests can be reused or reinforced, further increasing efficiency. The location itself becomes part of a repeated behavioral loop, not because it is optimal in all conditions, but because it has proven viable within the existing constraints. There are trade-offs. Urban nesting sites expose hawks to different risks compared to natural environments. Human infrastructure introduces hazards: glass surfaces, moving vehicles, and mechanical systems. However, these risks are often localized and predictable. Hawks adjust flight paths and movement patterns to minimize interaction with these elements. Noise levels in cities are higher, but they do not directly interfere with the core requirements of nesting. Visual detection remains the primary sensory input for hunting and threat assessment. As long as visibility is maintained, noise becomes a background condition rather than a limiting factor. Another trade-off involves thermal conditions. Buildings absorb and retain heat, creating localized temperature differences. Rooftops can become significantly warmer than surrounding areas during the day. This can influence incubation conditions. In some cases, increased warmth reduces the energy required to maintain egg temperature. In other cases, excessive heat requires behavioral adjustments such as shading or repositioning to prevent overheating. These adjustments are part of a broader pattern of behavioral flexibility. Hawks do not modify the structure of the building. Instead, they modify their use of it. They select specific locations, adjust their activity, timing, and alter their nesting materials based on available resources. The behavior is not a direct adaptation to urban environments, but a continuation of existing strategies applied to a different set of constraints. The presence of tall buildings does not create the behavior. It reveals how the behavior operates under new conditions. Over multiple seasons, these patterns stabilize. A building that consistently supports nesting becomes part of a larger network of urban habitats. Nearby buildings may host additional pairs, each occupying separate territories. The distribution is not random. It reflects the spacing required to maintain access to sufficient resources without excessive competition. From the street level, these patterns are not immediately visible. The activity occurs above the primary field of view, and the nesting sites are often positioned to minimize exposure. But the repetition is consistent. The same ledges, the same corners, the same approach paths. The behavior continues because the constraints remain stable. As long as tall buildings provide elevation, limited access, and proximity to food, they function as viable nesting sites. The materials may change, the surrounding environment may shift, but the underlying conditions that support the behavior persist. On that rooftop, the shallow depression near the ledge remains in place. The materials accumulate gradually. The two birds maintain their positions, adjusting only when necessary. Their presence is not constant movement, but consistent occupation. The structure beneath them does not resemble a cliff, but it fulfills the same requirements. Over time, the distinction becomes less relevant. What remains is a repeated decision pattern: select elevation, reduce access, maintain proximity to resources, and the behavior continues to function within the constraints that define it.